Testing, can you hear me? Testing again, can you hear me? Testing one last time. Alright, this video is public now. So, I'm going to be reading about introductory statistics again. And I'll be continuing from where I left off last time. Last time I studied about um, the normal distribution. Hold on. So, last time I studied about the normal distribution. This time I'm going to be just starting the next chapter. Sorry, last time I studied about the central limit theorem actually. This time I'm gonna start the next chapter, which is confidence intervals. So I'm planning to read chapter 8 and chapter 9 this stream. Suppose you were trying to determine the mean rent of a two-bedroom apartment in your town. You might look in the classified section of the newspaper, write down several rent listed, and average them together. You would have obtained a point estimate of the true mean. You're trying to determine the percentage of time you make a basket when shooting a basketball. You might count the number of shots you make and divide that by the number of shots you attempted. In this case, you would have obtained a point estimate for the true proportion. Use sample data to make generalizations about an unknown population. This part of statistics is called inferential statistics. Sample data helps us to make an estimate of the population parameter. We realize that the point estimate is most likely not the exact value of the population parameter, but close to it. After calculating point estimates, we construct interval estimates called confidence intervals. Should I update? You will learn to construct and interpret confidence intervals. You'll also learn a distribution called students T, how it is used with these intervals. You worked in a marketing department of an entertainment company. You might be interested in the mean number of songs a consumer downloads a month from Apple Music. If so, you could conduct a survey and calculate the sample mean and the sample standard deviation as you would use X bar to estimate the population mean and S to estimate the population standard deviation. Don't I have to do a basis correction with S? Sample mean is the point estimate for the population mean mu. The sample standard deviation S is the point estimate for the population standard deviation sigma. Each of X bar and S is called a statistic. A confidence interval is another type of estimate, but instead of being just one number, it is an interval of numbers. provides a range of reasonable values in which we expect the population parameter to fall. There is no guarantee that a given confidence interval does capture the parameter, but there is a predictable probability of success. Suppose for the Apple Music example, we do not know the population parameter mu, but we do know that the population standard deviation is sigma equal 1 and our sample size is 100. Then by the central limit theorem, the standard deviation for the sample mean is so sigma over root n. Uh, Population standard deviation is root n and our sample size is 100. Then by the central limit theorem, the standard deviation for the sample mean is this. The empirical rule which applies to bell-shaped distributions says that in approximately 95% of the samples, the sample mean x bar within two standard deviations of the population will be within two standard deviations of population mean mu. For our Apple Music example, two standard deviation is 0.2. The sample mean is likely to be within 0.2 units of mu. Because x bar is within 0.2 units of mu, which is unknown, then mu is likely to be within 0.2 units of x bar in 95% of the samples. Let me think about this. Mu, which is unknown. Then mu is likely to be within 0.2 units of x bar in 95% of the samples. Okay. Wait, suppose a population has a distribution like this, right? With this mu. Then we collect data. Maybe this is one average, this is one average. We are collecting averages. Maybe like this, like this. We're collecting averages. Our x bar supposed to be within 0.2 units of mu, right? Uh, X bar is within 0.2 units of mu. So these are all the possible, the histogram for different X bar intervals. Uh, so if there's an X bar here, yeah. Then mu is likely to be within 0.2 units of X bar in 95% of the sample. So in 95% of the samples, mu would be within 0.2 units. So for this example, let's say this, mu should be within 0.2 units 95% of the time. So for, okay, let's say 0.2 units is like this. Or okay. Population mean mu is contained in an interval whose lower number is calculated by taking the sample mean and okay, wait, my internet is fluctuating. Okay. Population mean is contained in an interval whose Lower number is calculated by taking the sample mean and subtracting 2 standard deviation, whose upper number is calculated by taking the sample mean and adding 2 standard deviations. Hold on. Okay. In other words, mu is between x bar minus 0. Okay, wait. Okay, I reconnected to my internet. Hopefully this works. So mu is within x bar minus 0.2 and x bar plus 0.2. Suppose that a sample produced a sample mean of x bar equal to 2, then the unknown population mean mu is between 1.8 and 2.2. We say that we are 95% confident that the unknown population mean number of songs downloaded from Apple Music per month is between 1.8 and 2.2. The 95% confidence interval implies two possibilities. Either the interval contains the true mean mu, or our sample produced an X bar that is not within zero point 0.2 of the true mean mu. First possibility happens 95% of the time of well-chosen samples. It is important to remember that the second possibility happens for 5% of the samples, even though correct procedure are followed. All right. Recall that a confidence interval is created for an unknown population parameter, like the population mean mu. Confidence intervals for some parameters have the form point estimate, margin of error, point estimate, or minus margin of error and plus margin of error. A confidence interval for a population mean, when the population standard deviation is known, is based on the conclusion of the central limit theorem that the sampling distribution of the sample mean follow an approximately normal distribution. Suppose that our sample has a mean of x bar equal to 10 and we have constructed the 90% confidence interval where EBM is equal to 5. If they're defining EBM later, you should not have mentioned this. To construct a confidence interval for a single unknown population mean mu, where the population standard deviation is unknown, we need x bar as an estimate for mu. We need the margin of error, and we need the margin of error. Here, the margin of error EBM is called error bound for a population mean. Error bound for mean. Sample mean x bar is the point estimate for the unknown population mean mu. Confidence interval estimate will have the form point estimate minus error bound plus error bound. The margin of error or error bound for a mean depends on the confidence interval. Confidence level depends on the confidence level. Confidence level is often considered the probability that the calculated confidence interval estimate will contain the true population parameter. However, it will be more accurate to state that the confidence interval is the percentage of the confidence intervals that contain the true population parameter. When repeated samples are taken, most often it is the choice of the person constructing the confidence intervals to choose a confidence interval of 90% or higher, because that person wants to be reasonably certain of their conclusion. Why don't we just take many means and then take the most frequent one? Why can't we do that? Also, I want to see some exercises. There's another probability called alpha. Alpha is related to the confidence interval. Alpha is the probability that the interval does not contain the unknown population parameter. Mathematically, alpha plus CL is equal to 1. Okay. Suppose we collect the data from a sample. We know the sample mean, but we do not know the mean for the entire population. The sample mean is 7, and the error bound for the mean is 2.5. Uh, Sample 7 error is 2.5. Okay. So minus 2.5 less 2.5. Calculating the values gives 4.5 and 9.5. If the confidence interval is 95%, then we say we estimate with 95% confidence that the true value of population mean is between 4.5 and 9.5. A confidence interval for the population mean with a known standard deviation is based on the fact that the sample means follow an approximately normal distribution. Suppose that our sample has a mean of x bar equal to 10, and we have constructed the 90% confidence interval 5 and 15 where EBM is 5. To get a 90% confidence interval, we must conclude the central 90% of the population of the normal distribution. If we include the central 90%, we give out a total of alpha is equal to 10% in both tails, 5 or 5% in each tail of the normal distribution. 95%. X bar is, okay, it says 2 over here. %90 confidence interval. To capture the central 90%, we must go out 1.64 standard deviations on either side of the calculated sample mean. The value 1.645 is the z-score from a normal standard probability distribution that puts an area of 0.9 in the center, an area of 0.05 in the far left tail, an area of 0.05 in the far right tail. So x bar plus minus c alpha times this. This is the this thing. What is the sample mean, right? Wait, sigma is, hold on. Sigma is the population standard deviation. Sigma, okay. This here is the sample mean, sorry, sample standard deviation. So we need to calculate C. It is important that the standard deviation must be appropriate for the parameter we are estimating. So in this section, we need to use the standard deviation that applies to sample means, which is sigma over root n. The fraction sigma over root n is commonly called the standard error of the mean. In order to distinguish clearly the Standard deviation for a mean from a population standard deviation. X bar is normally distributed. That is, X bar is normally distributed as mu and sigma over root n. This is a result of central limit theorem. When the population standard deviation mu is known, we use a normal distribution to calculate the error bound. To construct a confidence interval estimate for an unknown population mean, we need data from a random sample. Steps to construct and interpret the confidence interval are: calculate the sample mean x bar from the sample data. Remember, in this section, we already know the population standard deviation sigma. Find the z-score, calculate the error bound. Construct the confidence interval, write a sentence that interprets the estimate in the context of the situation in the problem. Yeah, I want to do an example. There is an example here. When we know the population standard deviation sigma, we use standard normal deviation to calculate the error bound EBM and construct the confidence interval. We need to find the value of z that puts an area equal to the confidence interval in the middle of the standard normal distribution. Z is distributed normally 0 and 1. The confidence level CL is the area in the middle of the standard normal distribution. CL is equal to 1 minus alpha. So alpha is the area that is split equally between two tails. Each of the tail contains an area equal to alpha over 2. The z-score has an area to the right of alpha over 2 denoted by z alpha over 2. Okay. C 0.025 is 0.025. Area to the left 0.975. The interpretation should clearly state the confidence level, explain what the population parameters being estimated, state the confidence interval, both endpoints. Estimate with blank percentage confidence that the true population mean is between blank and blank. Suppose scores on exams in statistics are normally distributed with an unknown population mean and a population standard deviation of 3 points. So scores on exams. So scores, I will use the white marker. What is this? This is example 8.2. Scores is normally distributed, unknown, and 3 units. 3 points, unknown population mean. A random sample of 36 scores is taken and gives a sample mean of 68. "36" and this over here is 68. Find the confidence interval estimate for the population mean exam score. Okay, we have this. So X mean would be normally distributed with the mu of the original and this over root 2. Well, in this case, it's 3, right? But we don't know this. I mean, we can find the z-score. Let me think. What is this mu over here? They said the mean is unknown, right? We cannot use mu. X bar is 68. N is 36. It's not root 2, it's root 36. Wait, sigma over root n gives you 3 over root 36, which is 3 over 6, right? So half. You have 36. Sorry, no. We have 68. 68. Standard deviation is half. And they're talking about 90%. 95% actually. For the population mean exam score. Find a 90% confidence interval for true population mean. 90%. When they say 90%, they mean one standard deviation away or two standard deviation away. In a normal distribution, in a normal distribution, how do we find the 90% interval? Is it this 1.645? 1.645, 0.645. Okay. 1.645. Um, what if 68? What if I take this normal distribution and shift it to this? So I shift the mean. I shift the mean to 68, right? And make it half. Minus 1.645. 68 plus 1.645. I take both of this. And then what about the standard what about the standard deviation of this distribution, which is half? Do I divide it by half? Um, Let me think. If I times it by half, I get 33 and 34.822. If I divide it by half, I'm times multiplying it by 2, right? Minus 1.645, 1.645. Formula for the confidence interval for an unknown population mean, assuming we know the population standard deviation is x minus z alpha, z alpha sigma over root n. Z, I have to multiply the z first, right? Yeah, I have to multiply the z first. I mean, I have to multiply the standard deviation first and then subtract it from 68. Then I get 67 and 68.8. What is this solution? The specific abortion rate for a cell phone, absorption rate for a cell phone measures the amount of radio frequency energy absorbed by the user's body when using the handset. What? Every cell phone emits RF energy. Different phone models have different specific absorption rate measures. To receive certification from the Federal Communications Commission for sale in the United States, the SAR level for a cell phone must be no more than 1.6 watts per kilogram. Table 8.1 shows the highest SAR level for a random selection of cell phone models as measured by the FCC. Okay. 1.6 is the highest, right? Find a 98 confidence interval for the true population mean for the specific absorption rates for cell phones. Assume that the population standard deviation is sigma is equal to 0.337. Isn't there a table we can see? How do we know? Group solution sheets, phrases, formulas. Yeah, table. Cumulative distribution function for standard normal deviation. Okay, this is a different website. Um, Area under the normal curve from 0 to x. What is this table? So from 0 to 0. I don't understand this table. Area under the normal curve from 0 to x. Shaded area of the curve represents the probability that x is between 0 and a. X is between 0 and a. What is the probability that x is less than or equal to 1.53? Look at 1.5 in the x column. Go right to the 0.03 column to find the value. Why are we going right to 0.03 column? So 1.5. 1.5. So this they're talking about. Why are we at, oh, wait, no. Okay, this area is 0.5, right? That's why we're adding 0.5. But what I don't understand is what is this 0.1, 0.2, 0.3? To obtain the final result. Oh, wait. This here is one decimal point. This here is a second decimal point. Okay. So this over here is 0.53. All right. So they said uh they were asking 98% confidence interval. Half of 98 is what? 49. 49. So I need to find exactly 49 over here. Or the closest to it. Okay, so it's this one right here, which is 2.3, 2.33, 2.33. So at 2.33, this area is 49, 0.49. 0 point. Okay, 2.4, 2.33 it is. 2.33. Assume that the population standard deviation is 0. Okay. You have 2.33. 8.3. So what is 2.33? That's the z score, right? We have this 30 cell phones. Now what? I have this 2.33. Multiply this with 2.33, right? Okay. And then and then the true population mean. They have to find the mean manually, like by adding them. 1.04 to 1.024. And then this. So I think this is the interval, right? Then 98% of the phones. 0.8809, 1.167. Why is it slightly inaccurate? Why do they say 2.3? Use your calculator, a computer, a probability table. They said 0.326. 0.33 is the maximum it goes to. So notice the difference in confidence intervals calculated in example 8.3 in the following tried example. These intervals are different for several reasons. They are calculated from different samples about different sizes, and the intervals were calculated for different levels of confidence. Even though the intervals are different, they do not yield conflicting information. The effects of these kinds of changes are the subject of the next section in this chapter. Changing the confidence level or sample size. Can this chapter is taking longer than expected? Suppose we change the original problem in example 8.2 by using a 95% confidence interval. Find a 95% confidence interval for the true population mean statistics exam score. 8.2, 8.2. Example. So what do they want us to do again? 95% confidence level. Find 95%. So what did we find before? 90%. And they want 95%. 95%. Half of 95 is 47.5. So 0.475. It's right here. 1.96. 1.96. Yeah. An example of 36 courses taken gives a sample mean of 68. And I already wrote this down, but I will write it again. 36 scores. 3 points. So half. Um, 67.02. 68.98. Wait. 67.02, 68.98. Explanation of 95% confidence in level. 95% of all confidence interval constructed in this way contain the true value of the population mean statistic exam score. Comparing the result, the 90% confidence interval is 67.18 and 68.82. The 95% confidence interval is this. 95% confidence interval is wider. Yeah, I mean, that makes sense. Working backwards to find the error bound or sample mean. When we calculate a confidence interval, we find the sample mean, calculate the error bound, and use them to calculate the confidence interval. However, sometimes when we read statistical studies, the study may state the confidence interval only. If we know the confidence interval, we can work backwards to find both the error bound and the sample mean. Finding the error bound from the upper value of the interval, subtract the sample mean, or from the upper value of the interval, subtract the lower value, and then divide the difference by 2. Finding the sample mean, subtract the error bound from the upper value of the confidence interval. Suppose we know that the confidence interval is this. You want to find the error bound. We know that the sample mean is 68. Okay, 68 is in the middle of these two, or perhaps our source only gave the confidence interval did not tell us the value of the sample mean. Sample mean is the middle of the two values, right? So we can just find it. But what else are we finding the error bound? Error bound is 0.28. And the sample mean is 68. If researchers desire specific margin of error, then they can use the error bound formula to calculate the required sample size. The error bound formula for the population mean when the population standard deviation is known is EBM Z and the sample mean. Sorry, the mean standard deviation. Formula for the sample size is n is equal to z square sigma square EBN square. Found by solving the error bound formula for n. In practice, we rarely know the population standard deviation. In the past, when the sample size was large, this did not present a problem to statisticians. They used sample standard deviation S to estimate sigma, proceeded as before to calculate a confidence interval with close enough results. Our statisticians ran into problems where the sample size was small. Small sample size caused inaccuracies in the confidence interval. William S. Gossett was a Guinness brewery in Dublin, Ireland ran into this problem. His experiment with hops and barley produced very few samples. His replacing sigma with S did not produce accurate results when he tried to calculate a confidence interval. He realized that he could not use normal distribution for the calculation. He found that the actual distribution depends on the sample size. This problem led him to discover what is called the student's T distribution. The name comes from the fact that Gossett wrote under the pen name student. Up until the mid 1970s, some statisticians used the normal distribution approximation for large sample sizes and used the student's T distribution only for sample sizes at most 30. With the graphing calculators and computers, the practice now is to use student's T distribution whenever S is used as an estimator for sigma or population standard deviation. If you draw a simple random sample of size n from a population that has approximately normal distribution with mean mu and an unknown population standard deviation sigma and calculate the t-score, t is equal to mean x minus mu over what is this? Over what? S divided by root n. What is S? Then the t-scores follow a student's t distribution with n minus 1 degrees of freedom. The t-score has a same interpretation as the z-score, measures how far x bar is from the mu, from its mean mu. For each sample size n, there is a different students distribution. Degrees of freedom n minus 1 come from the calculation of the sample standard deviation as this calculation requires n deviations. Because the sum of the deviations is 0, we can find the last deviation once we know the other n minus 1 deviations. The other n minus 1 deviation can change or vary freely. We call the number n minus 1 the degrees of freedom. The graph for the student's t distribution is similar to the standard normal curve. The mean is 0. The distribution is symmetric about 0. Student's t distribution has more probability in its tail than the standard normal distribution because the spread of the t distribution is greater than the spread of the normal distribution. Standard normal, I mean. The exact shape depends on the degrees of freedom. As the degrees of freedom increases, graph of students t distribution becomes more like the graph of the standard normal distribution. The underlying population of individual observation is assumed to be normally distributed with unknown population mean mu, unknown population standard deviation sigma. Size of the underlying population is generally not relevant unless it is very small. If it is bell shaped, then the assumption is met and doesn't need discussion. Random sampling was assumed, but that is completely separate assumption from normality. The grammar for the tcdf command, okay, they're talking about the calculator. So t score given the degrees of freedom and the right tailed probability. The table is very limited. So t scores. Probability less than the critical value. One 1.09, 1.95. Okay. The population standard deviation is not known. The error bound for a population mean is Ts over root n. T alpha over 2 is the t score with the area to the right equal to alpha over 2. T score for a two-sided test. Find the column corresponding to 1 minus alpha over 2. So alpha are these two. Alpha are these two area added together, right? Alpha 0.05. I think they should have written alpha over 2. And then 1 minus that gives the area before all. Okay. I need to see an example. How is the probability 318? How is it more than 1? How is the area more than 1? Suppose you do a study of acupuncture to determine how effective it is in relieving pain. You measure the sensory rate for 15 subjects with the results given. Use the sample data to construct a 95% confidence interval for the mean sensory rate for the population from which you took the data. Hold on. Let me think about this. Um, N is 15. Sample 8.8. 95% confidence interval. But I need to find the T score, right? S is the sample standard deviation, right? Yep. I have to calculate this sample standard deviation and the mean. I'll just take their value. We have 8.2267, S is 1 point. And then we can calculate this. But the thing is, how do we T alpha over 2? 0.95. Alpha over 2 is 0.025. T 0.025. The area to the right of T 0.025. Area to the left is this. Is there an inverse T calculator? Inverse CDF. T distribution. Fifteen. Um 15 degrees of freedom. No, we should write 14, right? It's degrees of freedom minus 1. 14. 14 degrees of freedom. I don't wait. Let me see if there is another table. No, I don't think they have it. Anyways, T T 0.025 is 2.14. 0.025 is like this area, right? 0.025, 2.14. 5. Do I have to just guess it? 2.14 is this area. 2.14 times it by S over root n gives 0.924. That's the error bound in the t distribution. So the mean x minus and during an election year, we see articles in the newspaper that state confidence intervals in terms of proportions or percentages. For example, a poll for a particular candidate running for president might show that the candidate has 40% of the vote within 3% points. Often, election polls are calculated with 95% confidence, so the pollster would be 95% confidence that the true proportion of voters are favored who favored the candidate would be between 0.37 and 0.43. Investors in the stock market are interested in the true proportion of stocks that go up and down each week. Businesses that sell personal computers are interested in the proportion of households in the United States that own personal computers. Confidence intervals can be calculated for the true proportion of stocks that go up and down each week and for the true proportion of households in the United States that own personal computers. The procedure to find the confidence interval, the sample size, the error bound, and the confidence level for a proportion is similar to that for the population mean, but the formulas are different. How do you know you're dealing with a proportion problem? First, the underlying distribution is a binomial distribution. If x is a binomial distribution, then x has this, where n is the number of trials and p is the probability of success. From a proportion, take x, the random variable, for the number of successes and divide it by n, the number of trials. Random variable p apostrophe, red p prime, is that proportion. When n is large and p is close to 0, is not close to 0 or 1, we can use normal distribution to approximate the binomial. So they would state confidence intervals in terms of proportion. 40% of the word within 3 percentage points. If P is not close to 0 or 1, we can use normal distribution to approximate the binomial. If we divide the random variable, the mean and the standard deviation by n, we get normal distribution of the proportions with P prime. Call the estimated proportion as the random variable. X over n P prime. Okay. P prime follows a normal distribution of our proportions. Confidence interval has the form P prime minus ABP, P prime plus ABP. ABP is the error bound for the proportion. P prime is equal to X over N. P prime, the estimated proportion of successes. X is the number of successes. N is the size of the sample. The error bound for a proportion is EBP Z alpha over 2 and then root P prime Q prime over N, where Q prime is equal to 1 minus P prime. This formula is similar to the error bound formula for a mean, except that the appropriate standard deviation is different. For a mean, when the population standard deviation is known, the appropriate standard deviation that use is alpha over root n. For a proportion, the appropriate standard deviation is root pq over n. However, in the error bound formula, we use root p prime q prime over n as the standard deviation instead of root p q over n. The error bound formula, the sample proportions p prime and q prime are estimates of the unknown population proportion p and q. The estimated proportions p prime and q prime are used because p and q are not known. The sample proportions p prime and q prime are calculated from the data. P prime is the estimated proportion of successes and q prime is the estimated proportion of failures. The confidence interval can be used only if the number of successes n p prime and the number of failures n q prime are both greater than 5. Suppose that a market research firm is hired to estimate the percentage of adults living in a large city who have smartphones. 500 randomly selected adult residents in the city are surveyed to determine whether they have smartphones. Of the 500 people surveyed, 421 responded yes, they own smartphones. Using a 95% confidence interval, compute the confidence interval estimate for the two proportion of adult residents of the city who have smartphones. So 500 people surveyed, 421 responded yes. Use 95% confidence interval. So X has a binomial distribution, but it can be approximated using the normal distribution. Um, NP root NP. And they said 95% confidence interval, right? 95%. Is this right? 1.96. 1.96. Um, I think 1.96 times it by sigma over root n. Is that what we have to do? But we don't know sigma. But we do know this, right? Sorry, we do know this. Uh, 0. So 1.96. 1.96 times it by the square root p times q. P times q. 421 over 500. Sorry, 500 minus 421. Well, this divided by 500, but it doesn't make a difference. So in 0.71489. 95% compute the confidence interval estimate. And the mean is n times p. Square root. Do I use 421 as the mean? So square root 421. Not square root, just 421. N times p. P is 421 over 500. But if I multiply that with 500, I will get 421 back. So it's 421 plus and minus. Is that right? Wait. Root n pq. P is this 421 over 500. Q is 500 minus 421 over 500. Then I multiplied by 500. So I get this 405 point. So it's 405 and 434. Is that it? Binomial n is 500. Probability of success is 421 over 500. Success. P prime is this. Q prime 1.96. Okay, but then what is this? EBP is q prime. It's 421 over 500. Q prime, which is 421. 1 minus that. This I understand. This I understand. Divided by n. Shouldn't it be multiplied by n? Shouldn't it be? Shouldn't it be this? Okay, let's say we are calculating this. So PQ over n. So P is 421 over 500. Q is this thing over 500. And then all of this divided by 500. Then I get 0.0319. And then P apostrophe minus ABP. Confidence interval for the two binomial population proportion is this. 81% and 87.4% of all adult residents of the city have smartphones. Calculating the sample size, if researchers desire specific margin of error, then they can use error-bound formula to calculate the required sample size. All right. What's this? Plus 4 confidence interval for P. There is a certain amount of error introduced into the process of calculating a confidence interval for a proportion. Because we do not know the true proportion for the population, we are forced to use point estimates to calculate the appropriate standard deviation of the sampling distribution. Studies have shown that the resulting estimation of standard deviation can be flawed. Fortunately, there is a simple adjustment that allows us to produce more accurate confidence intervals. Simply pretend that we have 4 additional observations. 2 of these observations are successes and 2 are failures. The new sample size then is n plus 4 and the new count of successes is x plus 2. Computer studies have demonstrated the effectiveness of this method. Should be used when the confidence level desired is at least 90% and the sample size is at least 10. Okay, let's just see one more problem and then I will end the stream. A political science student at a large university wants to estimate the percentage of students who are registered voter. He surveyed 500 and finds 300 are registered voter. Compute a 90% confidence interval for the 2% of students who are registered voter and interpret it. So first of all, firstly, we need to find this. We need to find population proportion. Uh, this is x over n. This is example 8.11. P is equal to, this here is not capital P, small p. 300 over 3 over 5. Q is 2 over 5. N is 500. So, uh, 90% confidence. This is 0.45, right? 0.45. I think 1.65 was it? 1.65. 3 over 3 times 2 over 5. No. Square root 2 over 5 times it by 3 over 5. This entire thing divided by 5. And then the probability of success 3 over 5. So 0.2385. What? 90% confidence interval. 8. P is x over n. Okay, let's see what they did. 3 over 6, 2 over 6, 1.645. Okay, it's 1.645. 1.645 root. It's divided by 500, right? Divided by 500. So it's between 0.564 and 0.636. Yep, between these two percentages. I think I will end this stream here then. And yeah, I thought I would be able to study the next chapter as well, but I think this chapter was pretty confusing for me. So I will keep this for the next stream. Right, I will end the stream here and yeah, I will see you guys next time. Bye.